Welcome, friends, I'm happy you're here today. Together we'll follow the journey of a star from its birth in a cradle of gas and dust to its brilliant years of shining and finally to its quiet or explosive end. If you enjoy these gentle voyages through the cosmos, please like, subscribe or share. Thank you. In the quiet dark, a molecular cloud lies like a veiled continent of dust and gas, colder than breath, older than memory, its temperature near 10 to 20 Kelvin, where heat scarcely stirs and light cannot easily pass. Here gravity works patiently, not as a shove, but as a soft, continual leaning, drawing matter into slightly denser knots that deepen their own pull. The grains are minute shards of silicate and carbon, each wrapped in thin ices of water, carbon dioxide and methanol, and they float in numbers so large that a handful would outcount cities, yet their collective shadow is what dims starlight and marks the cloud's outline on the sky. The gas is mostly hydrogen, the simplest breath of the cosmos, and second to it helium with trace atoms and molecules that write their faint signatures into radio waves. Carbon monoxide announces its presence in a line near 115 gigahertz, and astronomers track that whisper to sketch the ribs and hollows of this cold cathedral. Pressure and gravity converse here in long syllables. Thermal motion tries to smooth the clumps while gravity seeks to sharpen them. When a parcel of gas grows large and dense enough that self-gravity overwhelms the ability of heat to hold it up, it crosses the classic threshold known as the gene's instability, and the parcel begins to fall inward upon itself. The fall is not a plunge, but a surrender because cooling keeps pace with compression. Molecules radiate away energy and quanta that leave the cloud and take heat with them, so the interior stays cool enough to continue collapsing like a lung, learning to exhale more deeply with each breath. Yet the cloud does not collapse as one it fragments into many seeds, because turbulence ripples through it in tangled flows, and magnetic fields thread the darkness like invisible wires, slowing and guiding motion through a drag called ambipolar diffusion, as neutral gas slides past ions that remain tethered to field lines. It is a dry observation, but one that comforts the mind. Gravity moves fastest here by barely moving at all. In the time a person takes to draw a single breath, nothing in this cloud changes, and in the time a forest grows old, almost nothing does. Another soft irony lies in the way cold does the work that heat would claim. By keeping the cloud-chilled radiation losses allow gravity to persist, so that not burning builds the future burner. A third sits inside the phrase star formation efficiency, a grand term for a modest yield. Only a small fraction of a cloud's mass becomes stars, most of it returning to silence so that the universe arrives at light by spending generously on darkness. The densest knots called prestellar cores grow opaque at their centers as dust becomes thick enough to trap its own heat. Pressure slowly rises, the inward fall slows locally, and a warm kernel begins to emerge, not yet a star but something that leans toward one. Around each forming center, angular momentum never zero asserts its quiet rule. The infalling gas cannot aim for the center directly, so it spirals and spreads into a disk whose plane remembers an initial nearly random tilt. The disk is neither bright nor smooth. It is a slab of pebbles, grains, and gas in shear, with temperatures that may rise from a few tens of Kelvin in the outer reaches to a few hundreds closer in. Its inner rim glows in the infrared, while the outer shadows drink starlight from beyond and remain cold enough to preserve fragile ices. Along the poles of the forming center, matter finds an exit. Infall collides with the growing pressure and magnetic structure, and is redirected outward as bipolar outflows and narrow jets that run for light years at speeds of tens to hundreds of kilometers per second, carving cavities whose walls shine faintly in forbidden lines of oxygen and sulfur when eventually lit from within. These outflows perform a balancing service. They carry away angular momentum that would otherwise bottle the collapse. They clear the cocoon so that radiation can escape, and further cooling continue. and they mark in their straight, stubborn lanes the hidden presence of a centre still too swaddled to be seen in visible light. The density at the heart climbs from thousands to millions of particles per cubic centimetre, and the central temperature approaches a few thousand Kelvin, enough for heat to matter, but not enough to fuse, so the object remains a protostar, a word that admits its own humble status. It shines by contraction, not by burning its luminosity drawn from the energy of infall and the release of gravitational potential, and this light streams outward through dust that absorbs and re-radiates it in longer wavelengths. The entire process is slow, measured in hundreds of thousands to a few million years, a steady hush in which outer shells keep joining, inner shells keep settling, and the disk keeps feeding the centre, with little surges of material that may change its brightness by small factors over months or years. Within the extended cloud, clumps do not agree on a schedule. Some begin to fall while others hover near balance, and still others dissolve back into the diffuse medium, when a passing shock or a brush of radiation warms them beyond the point of return. The mixture of scales and tempos makes a cluster, not a single star, and the eventual siblings will range widely in mass because small differences cascade across long times. It is enough to note one stable fact: mass decides what follows. A more massive seed compresses more strongly and draws material more rapidly. A less massive seed dawdles and starves more easily. The cloud by its own nature contains all those fates in embryo. At this earlier stage the mysteries are thoroughly polite and will not raise their voice. No one fully knows how interstellar turbulence is driven and sustained over long spans, or how exactly magnetic fields, gravity and turbulence divide the labour of fragmentation under different metallicities and local histories. The ratios of rotation and magnetic field strength that set disk sizes and jet collimation remain a little murky, and the ways tiny dust grains first stick, grow, and settle in disks are still being clarified by observations and models that improve each year. The diary of this darkness is written in wavelengths the human eye cannot see, and yet the tale is testable, and often retold arrays of radio dishes trace carbon monoxide, ammonia, and nitrogen-bearing molecules. Far infrared telescopes weigh the dust by its glow. Polarimetry sketches the direction of magnetic fields by the slightly preferred alignment of elongated grains, and deep images reveal filaments braided like rivers that branch and recombine into hubs where cores gather. Another dry observation as soft as nightfall. The path to luminous day is paved by emissions that look like silence to the naked eye. In the end, the core at the centre reaches the moment when its interior no longer cools as fast as it compresses. Radiation is trapped more effectively. The temperature climbs, the equation of state stiffens, and the infall reorganizes into a central object supported by rising thermal pressure. The surrounding envelope continues to land upon it through the disk, and the disk continues to pass the gift inward as spirals of gas and dust move through. A nascent wind begins driven by magnetized rotation, and heat an early clearing of the throat that will one day speak with more confidence. For now there is only the softest promise of what will come, a seed that does not yet burn, a disk that does not yet shine in scattered blue light jets that do not yet meet illuminated walls. Only took a few 100,000 years to gather a candle that is not yet aflame. Only took a continent of coal to sketch a small warm room. Only took a web of invisible lines to tell matter where to fall. The cloud does not know it is making a star. It only answers gravity with a long, slow yes. The molecular cloud does not vanish when one core grows warmer. Instead, its fragments continue to draw in their own slow weather, each collapse isolated by distance yet linked by origin. Within one such knot, the centre has passed from the invisible chill of prestellar quiet into the dim light of a true protostar. It is still wrapped in dust, but the balance within has shifted. gravitational energy converts to heat. Heat thickens the gas, and pressure begins to push back against the inward fall. Around it, the circumstellar disk has widened its inner regions warmer, its outer lanes still cold and dark, their particles coated in ices that one day may deliver water and organics to worlds not yet imagined. The disk rotates with a shear that drags gas along the magnetic field lines threading it, launching bipolar outflows that pierce the surrounding envelope with narrow columns of material. These outflows are neither violent nor sudden, but steady and persistent, a slow siphon of excess spin that allows the infall to continue. In visible light, the scene remains dark, but in the infrared, the core glows its radiation, warming nearby dust and revealing itself in surveys. This is the stage known as the T-Tauri phase for stars of low and intermediate mass, named for the variable prototype in Taurus, whose brightness waxes and wanes as accretion varies. At the surface, star spots regions of cooler temperature driven by magnetic activity turn slowly in and out of view, changing the light by small degrees. The winds here are young, but they are already shaping the final mass of the star by pushing away gas from the disk's upper layers and from the inner edge where the stellar magnetosphere disrupts the disk's direct flow. Ironically, the star's earliest sustained breath is an act of self-limitation. By expelling gas, it prevents itself from growing too large, and by disturbing the disk it reduces the inflow that might otherwise feed it for longer. A second irony lies in the variability itself, for the fluctuations are unpredictable, yet repeat in broad rhythm, a restless prelude to the far longer stillness of the main sequence. The third irony is that even as light increases, the star remains hidden from most human eyes, its growing radiance buried in dust that only later will scatter it into space. Inside the protostar, the core temperature rises toward the critical mark of about 10 million Kelvin, where hydrogen nuclei protons can overcome their mutual electrostatic repulsion and begin the fusion that will define stellar life. In stars like this, the main process will be the proton-proton chain, where hydrogen fuses to helium through a series of steps involving deuterium and positron emission, producing neutrinos and gamma-ray photons. For more massive stars, the carbon-nitrogen-oxygen cycle will dominate, using carbon-nitrogen and oxygen nuclei as catalysts to convert hydrogen to helium at higher core temperatures. But in this phase, the reactions are not yet fully ignited. Instead, the protostar radiates energy from gravitational contraction, a process described by the Kelvin-Helmholtz timescale, which for a solar mass star is tens of millions of years. As the surface contracts, the luminosity may remain constant or even increase slightly, because the shrinking surface becomes hotter, moving the spectrum from far infrared toward the red and eventually into the optical range. The surrounding envelope thins as more material accretes onto the star or is pushed away by winds and outflows, and the once opaque cocoon develops translucent gaps. Through these windows, starlight begins to escape, scattering off dust in the cavity walls, creating faint reflection nebulae with soft blue glows. The disk's fate depends on the balance between accretion wind erosion and possible forming planets. In many systems, gaps appear in the disk within a few million years, and accretion slows until the disk dissipates entirely. Still, at this moment in the star's life, the disk remains a major feature, feeding the star with inward spiraling gas, whose infall is often channeled along magnetic field lines directly onto the poles, creating localized hotspots that brighten and fade with the rotation. Observations in ultraviolet and X-ray light reveal bursts of activity from magnetic reconnection events in the star's corona, another sign that this young object is already complex in its magnetic behavior. These emissions can influence the chemistry of the disk's surface layers, altering the path toward planet formation. A quiet mystery persists about how exactly magnetic braking operates in these early phases, while magnetic fields are thought to remove angular momentum from the collapsing cloud, and the forming disk, the efficiency of this process in various environments, remains under study, as does the role of non-ideal magnetohydrodynamic effects like ambipolar diffusion and Hall drift in shaping disk sizes and structures. Another uncertainty concerns the distribution of stellar rotation rates emerging from this phase. Some stars spin rapidly, others slowly, and the factors controlling this spread are not yet fully clear. The winds at this stage are cooler than those of mature stars often measured at a few hundred kilometers per second, but still sufficient to clear the surroundings over tens of thousands of years. In the cavities carved by these flows, gas density drops and the radiation from the protostar can travel farther, heating and ionizing small regions that mark the beginning of its influence on the local interstellar medium. This feedback may also trigger or suppress further star formation nearby depending on the conditions. It is a quiet irony that the first true effect of a forming star on its environment may be to prevent other stars from forming too close, as the winds and radiation disperse gas before it can collapse. Over time, the balance between infall and outflow tips toward the latter. When the supply from the envelope diminishes to the point that accretion rates fall to negligible levels, the star becomes optically visible, for the first time no longer entirely shrouded in its natal material. Its spectrum now shows absorption lines characteristic of its surface temperature and gravity, placing it on the Hertzsprung-Russell diagram along the nearly vertical pre-main sequence tracks. For a solar mass star, this is the Hayashi track, where the star contracts at nearly constant temperature until it approaches the main sequence. More massive stars follow the Henye track, moving horizontally in the diagram as they heat up before settling. Throughout this process, the internal structure changes, convection zones deepen or recede, radiative cores develop, and the path of energy from the center to the surface evolves toward the configuration it will maintain during most of its life. The moment of ignition is not heralded by a visible flash, but by a slow stabilization, when hydrogen fusion in the core produces enough energy to exactly balance the inward pull of gravity. The contraction halts. Hydrostatic equilibrium is reached and the star takes its place on the main sequence, where it will remain for the majority of its lifetime. For now, in this young stage, just before that balance, there is still motion, still contraction, still the final acts of a long arrival. The star is brighter than it will be for much of its main sequence life, its radius slightly larger, its surface cooler, but its interior now ready for the sustained steady burn of fusion. Only took millions of years to clear the fog and show a light. Only took a storm of magnetic loops to quiet the spin enough for balance. Only took a disk, a wind, and a collapse to make the smallest, most enduring fire in the sky. The protostar rests on the brink, its light still young, its story still mostly ahead, but the path is set. The star now crosses the quiet threshold from contraction into true stellar life, the invisible mark where core temperatures sustain hydrogen fusion, continuously replacing the energy lost from the surface and halting the slow inward fall. This is hydrostatic equilibrium, a precise balance between the inward pull of gravity and the outward pressure of hot gas and radiation from the core. For a star of solar mass, the core temperature holds near 15 million Kelvin, and the proton-proton chain reaction dominates, joining hydrogen nuclei into helium through a sequence that produces neutrinos, gamma-ray photons, and the subtle alchemy of heavier isotopes like deuterium and helium-3. Each photon born in the core will scatter countless times in the dense interior, taking hundreds of thousands of years to wander outward before emerging as visible light. Above the core lies a radiative zone where energy moves outward by photon diffusion, and beyond that a convective zone churns like a vast slow ocean, carrying heat to the surface in rising and falling cells. The surface temperature of a solar-type star rests around 5,800 Kelvin, emitting a spectrum peaking in the visible range, white to human eyes but rich with subtle absorption lines from atoms and ions in the photosphere. In massive stars where the carbon-nitrogen-oxygen cycle runs more efficiently at higher temperatures, the balance is similar but the lifetimes are shorter, the luminosity is greater, and the colours shifted toward the blue. The main sequence is not a sudden transformation, but a settling the star easing into a long, steady rhythm that will last for billions of years in the case of small and medium stars, and only millions for the largest. This long stillness is one of the great ironies of stellar life after a turbulent, irregular birth. The star spends the vast majority of its existence in apparent changelessness, a quiet so prolonged that from a human perspective it seems eternal, though in truth hydrogen in the core is slowly being consumed. Another irony is that the very stability that makes the star reliable also seals its fate, for the fuel it burns so evenly cannot be replenished at the core. The helium ash builds up inert under these conditions, while fusion proceeds only in the surrounding hydrogen shell. A third irony rests in the fact that no two stars hold their stillness for the same length of time, for lifetime scales, with mass to a steep negative power. The more massive the star, the shorter the life, as though abundance hastens its own loss. The main sequence position of a star on the Hertzsprung-Russell diagram is determined chiefly by its mass, with secondary influences from chemical composition, rotation rate, and magnetic activity. Metallicity. The fraction of mass in elements heavier than helium affects opacity, and thus the balance between radiation and convection, in the envelope subtly altering the star's luminosity and surface temperature. Rotation can flatten the star slightly at the poles, redistribute surface temperature, and mix material between layers, affecting the rate of hydrogen consumption. Magnetic fields often generated by convection and rotation in a stellar dynamo can influence stellar winds, which in turn remove angular momentum over time, gradually slowing the rotation in a process called magnetic braking. The quiet mystery here is not the existence of these influences, but the detailed mapping between them and the full diversity of stellar behavior. How exactly rotation rates, metallicities, and initial magnetic field strengths interact to shape a star's evolution remains an area of active study, as does the long-term stability of convection patterns and the role of differential rotation deep inside the radiative zones. For most of its main sequence life, the star changes very little in appearance. The radius increases slowly, the surface temperature may shift slightly, and the luminosity rises by a few tens of % over billions of years. In the Sun, for example, models indicate it was about 70% as bright 4.5 billion years ago. As it is today, a gradual brightening that has influenced planetary climates. Stellar winds carry mass away at a low rate for a solar-type star, about 1/100th of the mass of Earth each year. But over gigayear spans, this can still amount to measurable loss. In more massive stars, winds can be fierce, removing a significant fraction of mass during the main sequence, particularly in the case of luminous blue variables and O-type stars whose radiation pressure on spectral lines drives powerful outflows. On the surface, granulation patterns reveal the tops of convective cells, each hundreds to thousands of kilometers across, evolving over minutes in the case of the Sun. Sunspots and star spots, cooler regions of concentrated magnetic fields, wax and wane in cycles, their distribution and size altering the star's brightness slightly. Inactive stars, flares and coronal mass ejections can release immense bursts of energy, heating plasma to tens of millions of Kelvin and emitting high-energy radiation. Such events can affect surrounding planetary atmospheres, strip lighter gases from small worlds, or contribute to complex auroral displays on larger ones. Yet all of this occurs against the backdrop of overall stability. The star remains in its main sequence phase, an anchor of consistency in an evolving galaxy. The star's interior is a silent archive of nuclear physics in action. In the core, every second, hundreds of millions of tons of hydrogen are converted into helium-releasing energy, according to Einstein's relation between mass and energy. The helium nuclei settle toward the center, slowly building a region where no hydrogen remains. Surrounding that core, hydrogen continues to fuse in a shell, though in early main sequence stages this shell is small and its contribution modest. The balance between pressure and gravity is so exact that a change in core temperature of a fraction of a percent would disrupt it. Yet the self-regulating nature of fusion ensures stability. If the core temperature rises, fusion rates increase, expanding and cooling the core. If it drops, fusion slows, the core contracts, and the temperature rises again. This thermostatic behavior is one of the reasons main sequence stars are so enduring. For all this precision, the seeds of future change are present from the first moment of equilibrium. As helium accumulates in the core, the mean molecular weight increases, and to maintain pressure balance, the core contracts and heats, slightly increasing the fusion rate in the surrounding hydrogen shell. This gradual shift causes the slow brightening observed over time. The main sequence is thus not a fixed point, but a gentle slope toward a future departure. Still, from the perspective of the present, the star appears timeless, its photons crossing space to worlds and clouds alike, its light joining the vast sum of starlight that defines the character of a galaxy. From a cluster's zero-age main sequence to its turn-off point, the pattern repeats across the sky, mapping the shared physics of nuclear fusion and hydrostatic balance. Only took a handful of fundamental forces to hold the shape for billions of years. Only took the smallest of particles to fuel the largest of fires. Only took stillness to become the busiest furnace in the neighborhood of the galaxy. In the expanse of cosmic time, the main sequence is the deep breath between the restless arrival and the inevitable departure, a steady burning that writes itself into the chemical and photonic history of the universe, without hurry, without pause, without the need to be noticed. In time measured not by days or years, but by hundreds of millions or billions, the steady burning of hydrogen in the core shifts the balance within the star. Helium ash, inert under current conditions, collects at the center, while hydrogen fusion migrates to a shell around this growing core. As the helium core's mass increases, gravity compresses it further and the temperature rises. The outer layers of the star respond to the subtle increase in core luminosity by expanding and cooling, a process that moves the star off the main sequence on the Hertzsprung-Russell diagram. For a solar-type star, this shift marks the beginning of the subgiant phase, a quiet prelude to the swelling that will follow. The radius grows, the surface temperature falls, and the color shifts toward the orange or red, even though the total luminosity may continue to climb. Inside the hydrogen-burning shell becomes the primary energy source, producing more energy than the core once did, driving expansion of the envelope while the core contracts. In massive stars, this transition occurs more rapidly and at higher luminosities, and the path on the diagram can be more horizontal before the star ascends into the giant branch. The irony of this stage is that while the core shrinks and heats, the outer layers expand and cool, as though the heart were tightening even as the skin loosens. Another irony lies in the source of brilliance. The hydrogen fusion is now occurring in a smaller region, yet it produces more energy than before, an intensification that results from the increased pressure and temperature in the shell. The third irony is that the expansion of the envelope can cause the star's atmosphere to become tenuous and transparent enough in places for light from deeper layers to escape more easily even as the surface cools. For low and intermediate mass stars, the subgiant phase is followed by a rapid ascent up the red giant branch. The core, composed of helium and supported only by electron degeneracy pressure, once it cools enough to lose thermal support, cannot expand to relieve the pressure of contraction, so the temperature climbs steeply. Surrounding it, the hydrogen-burning shell pours energy outward, inflating the envelope to tens or hundreds of times its original radius. The surface temperature drops to around 3000 Kelvin, giving the star a deep red hue. The luminosity can reach hundreds or even thousands of times the main sequence value. This vast swollen atmosphere is convective with enormous cells that can span a significant fraction of the stellar radius, transporting energy from the hydrogen-burning shell to the surface. Stellar winds intensify, carrying mass away at rates far higher than during the main sequence, stripping the star of its outer layers over time. For more massive stars, the post-main sequence path leads to the blue supergiant or red supergiant phases, depending on mass and composition. In red supergiants, the radius can grow to 1,000 times that of the Sun, large enough to engulf the orbits of planets. The surface gravity becomes so low that material can be lost with little provocation, feeding circumstellar envelopes of gas and dust. Blue supergiants, by contrast, retain hotter surfaces, but their interiors are already undergoing complex burning in multiple shells. In all cases, the change in structure marks a shift in the internal energy transport. As the core contracts and heats, new fusion reactions become possible. But in lower mass stars, the helium core is not yet hot enough for fusion to begin. Here lies a quiet mystery that still draws investigation. The detailed interplay between convection rotation and mass loss in these expanded envelopes is difficult to model, and small differences can lead to significant divergences in the later path. The mixing of material from deep within to the surface, known as dredge-up, can alter surface abundances, revealing products of nuclear burning such as carbon, nitrogen, and lithium. The timescales of these phases vary enormously with mass. A star of one solar mass may spend over 1 billion years in the main sequence, but only a few hundred million ascending the red giant branch, while a star of 10 solar masses may traverse these stages in mere tens of thousands of years. The gravitational contraction of the core continues until the temperature reaches about 100 million Kelvin, at which point helium fusion ignites through the triple alpha process, converting helium into carbon and releasing energy. In stars less than about 2¼ solar masses, the helium ignition occurs explosively in what is called the helium flash, a sudden onset of fusion in a degenerate core that releases an enormous amount of energy in seconds. Yet the energy goes into lifting the degeneracy and expanding the core, so the event is hidden from external view, leaving no optical signature. This is perhaps the most understated transformation in the star's life, an interior cataclysm that the surface does not betray. In more massive stars, helium ignites smoothly without a flash, as the core is not degenerate at ignition. Once helium burning begins, the core expands and cools slightly, and the hydrogen-burning shell moves outward. The star's radius contracts somewhat, the surface temperature rises, and the luminosity decreases slightly compared to the tip of the red giant branch. The star now occupies the horizontal branch for lower mass stars, or the blue loop for intermediate mass ones, where it remains stable for tens to hundreds of millions of years, while helium is fused into carbon and oxygen in the core. The irony of the horizontal branch is that it represents another pause, another long stillness, but it comes after such a rapid and dramatic swelling that its quiet seems almost improbable. The second irony is that while the core is now fusing heavier elements, the energy output can be less than during the shell burning phase that preceded it. The third irony is that the star's position on the diagram during this phase can mislead an observer unfamiliar with its history, as it lies not far from the main sequence in temperature, but is powered by entirely different processes. Helium fusion proceeds until the core is filled with carbon and oxygen elements that cannot fuse at the temperatures and pressures available in a low-mass star. As the helium in the core is exhausted, the star once again begins to fuse hydrogen and helium in shells around the core, leading to renewed expansion and cooling of the surface. This marks the entry into the asymptotic giant branch phase, a stage that will see intense mass-loss thermal pulses and the eventual shedding of the envelope into a planetary nebula. But for the moment in this section's view, the star has only just completed the transition from main sequence stability into the first great departure, a swelling and brightening that changes its face to the galaxy. Only took billions of years to prepare a few million of transformation. Only took a hidden flash to rearrange the heart of a giant. Only took the faintest outer cooling to announce the greatest inner heat. The star has stepped into the second act of its life, where change comes not in sudden bursts, but in vast, slow movements, each one shifting the balance between core and envelope, between burning and cooling, between the gravity that holds and the light that escapes. In the asymptotic giant branch phase, the star's structure becomes layered in a way that seems almost deliberate, though it is only the outcome of physics arranging itself according to temperature, density, and available fuel. At the very center lies an inert core of carbon and oxygen compressed to extraordinary densities and supported by electron degeneracy pressure, which resists further collapse without requiring heat. Around this core burns a thin shell of helium fusing into carbon and oxygen through the triple alpha process, and beyond that, farther out, a shell of hydrogen fuses into helium. These shells do not burn at the same rate. The hydrogen shell operates more steadily, while the helium shell ignites episodically in powerful flashes called thermal pulses. Each pulse lasts only a few hundred years but can release energy comparable to the star's entire output during quiescent periods. The result is a slow rhythm of swelling and contracting in the outer layers, a breathing that takes tens of thousands of years per cycle. The irony here is that the most noticeable changes in the star's outer appearance are driven by events deep within, yet those events are invisible except through their consequences. Another irony is that these immense pulses capable of restructuring the envelope occur during a stage when the star is already losing mass at prodigious rates, up to 1/10,000th of a solar mass per year. A third irony is that while the core grows more compressed and hotter, it moves ever closer to a state in which no further fusion can occur even as the outer layers expand toward the edge of gravitational binding. The atmosphere of an asymptotic giant branch star is cool enough around 2,000 to 3,000 Kelvin for molecules to form, and dust condenses in the outermost regions. These dust grains, pushed outward by the pressure of the star's intense light, help drive the stellar wind that strips the envelope. The wind carries carbon, nitrogen, and S-process elements into the surrounding space, seeding the interstellar medium with material that will later be incorporated into new stars and planets. The S-process, or slow neutron capture process, occurs during helium shell flashes, when high temperatures enable reactions that produce free neutrons, which are then captured by atomic nuclei over relatively long timescales, building heavier elements step by step. This process is a primary source of elements like strontium, barium, and lead in the universe. Yet the details of how these elements are dredged up to the surface remain an area of active research, as the interplay between convection pulsations and mass loss is complex and sensitive to initial conditions. The dredge-up episodes mix material from deep layers to the surface, changing the observed composition of the star's atmosphere. In some stars, carbon is brought to the surface in quantities that make it more abundant than oxygen, producing carbon stars whose spectra are rich in molecular bands of carbon compounds. Observationally, these stars are bright in the infrared because of their cool temperatures and surrounding dust shells, and they are often variable in brightness due to large-scale pulsations that cause the star to swell and contract. The period of variability can range from 100 to 1,000 days, and the amplitude can be significant enough to be visible to the unaided eye over months. The physical driver of these pulsations is still not entirely resolved, with contributions from both fundamental mode oscillations of the extended envelope and complex interactions with convection and shocks in the atmosphere. The winds of asymptotic giant branch stars are slow compared to those of massive hot stars, often only 10 to 20 kilometers per second, but their density is high, and over a few 100,000 years they can remove the entire envelope. This gradual loss reveals the compact core beneath, and when the envelope mass falls below a certain threshold, the star can no longer sustain fusion in the shells. The remnant contracts and heats rapidly moving across the Hertzsprung-Russell diagram toward higher temperatures at nearly constant luminosity. The ultraviolet radiation from this hot core ionizes the expanding shell of gas, producing a planetary nebula, a glowing bubble of ionized gas with intricate shapes sculpted by the interaction of stellar winds, magnetic fields, and possibly binary companions. These nebulae are transient, lasting only tens of thousands of years before dispersing into the interstellar medium, but in that time they can be strikingly beautiful, with emission lines from hydrogen, oxygen, and nitrogen, giving them vivid colors in images. The planetary nebula stage is brief on stellar timescales, and the core now exposed cools and fades as a white dwarf. This object is typically about the size of Earth, but with a mass comparable to the Sun, yielding an average density of about 1,000,000 grams per cubic centimeter. Supported entirely by electron degeneracy pressure, it will no longer fuse elements, but will radiate away its residual heat over billions of years, slowly cooling toward invisibility. In the case of a star born with mass above roughly 8 solar masses, the asymptotic giant branch phase is replaced by more advanced nuclear burning stages, where carbon, neon, oxygen, and silicon are fused in successive shells until an iron core forms. Iron cannot be fused into heavier elements without consuming energy, so once the core reaches the Chandrasekhar limit, about 1.4 solar masses, it collapses under gravity, triggering a core collapse supernova. The details of these final stages for massive stars will come later, but for the lower mass star here, the asymptotic giant branch is its last act of active nuclear fusion. It is a quiet mystery why mass loss rates vary so much among stars with similar initial masses and compositions. Some lose their envelopes quickly, others more gradually, and the causes may lie in subtle differences in pulsation modes, magnetic activity, or the presence of unseen companions. Observations from infrared space telescopes have mapped thousands of asymptotic giant branch stars in the Milky Way, and nearby galaxies showing their contribution to galactic chemical enrichment. Models of galactic evolution must include these stars to match observed abundances, underscoring their importance despite their relatively short lifespans. Only took a few 100 million years to build the core that will now persist for billions. Only took the steady breath of shell burning to prepare the sudden exhalation of a nebula. Only took a slow wind of dust and molecules to reshape the chemistry of the galaxy. The asymptotic giant branch is a stage of grandeur and generosity, where the star gives back to the cosmos what it once drew from a molecular cloud, enriched now with the products of its own long labour. It is also a stage of endings where the path narrows toward one of only a few possible fates, each determined by the mass the star began with, and the mass it has left behind. In this long twilight the surface cools, the winds rise, the core contracts, and the star's shape becomes less certain as pulsations and dust obscure its exact edges. It is a time when the boundaries between star and space blur, when what was once a single luminous body becomes a system of light, gas, and dust in slow motion, bound together only briefly before drifting apart. For stars of greater initial mass, the path beyond the main sequence is both more rapid and more complex, shaped by the capacity of higher core temperatures and pressures to fuse elements beyond helium. Once hydrogen in the core is exhausted, these stars, often more than 8 times the mass of the Sun, do not pass through an extended red giant branch in the same manner as smaller stars. Instead, they quickly ignite helium fusion in the contracting core without degeneracy, fusing helium into carbon and oxygen through the triple alpha process. Surrounding this core, hydrogen continues to burn in a shell, and above it the envelope may expand to form a red supergiant or remain more compact as a blue supergiant, depending on mass rotation, metallicity and internal mixing. The irony here is that the more massive the star, the shorter each phase becomes, as higher pressures accelerate the fusion rates dramatically. A star 10 times the mass of the Sun may spend only a few million years in the main sequence, and mere hundreds of thousands in each subsequent burning stage. A second irony is that these colossal stars, capable of producing luminosities hundreds of thousands of times that of the Sun, are also among the most unstable, prone to shedding mass in violent winds and eruptions that can remove much of their outer layers before the core has finished its sequence of fusions. The third irony is that while their outer appearances can vary, swelling into cool vast supergiants or remaining as hot luminous blue points, the processes deep inside converge toward the same inevitable end, the formation of an iron core. After helium is exhausted in the core, the temperature and density rise enough to ignite carbon fusion, which proceeds through reactions such as carbon-carbon fusion to produce neon, sodium and magnesium. Carbon burning requires temperatures of about 600 million Kelvin and can last only a few thousand years in a massive star. Once carbon in the core is depleted, the process repeats, the core contracts. The temperature rises and neon fusion begins producing oxygen and magnesium, lasting only a year or so. Oxygen burning follows at temperatures near 1.5 billion Kelvin, creating silicon, sulfur and other intermediate mass elements enduring mere months. Finally, silicon burning at about 2.7 billion Kelvin produces iron group elements, including iron, cobalt and nickel, over a span of only days. Each of these stages occurs in shells around the core as lighter elements continue to burn in layers above, creating an onion-like structure where hydrogen burns at the outermost layer, helium beneath it. Then carbon, neon, oxygen and silicon in successive shells, inward ending with an iron core at the center. The quiet mystery in these late stages is the exact role of convection rotation and magnetic fields in mixing materials between shells, which can alter burning rates, lifetimes, and the yields of heavy elements. Another uncertainty lies in how mass loss through winds or binary interaction changes the final structure before collapse. These final burning phases are prodigiously luminous, but invisible in the sense that most of the energy is radiated from the surface in the same spectral range as before. The star's outer layers do not reveal the furious pace of nuclear transformations inside. The iron core that results from silicon burning is fundamentally different from all that came before. Fusion beyond iron does not release energy. Instead, it consumes it. As the core approaches the Chandrasekhar mass of about 1.4 solar masses supported by electron degeneracy pressure, the density and temperature become so extreme that electrons are captured by protons in atomic nuclei, producing neutrons and neutrinos in a process called electron capture. This reduces the electron degeneracy pressure, causing the core to collapse catastrophically in a fraction of a second. The collapse proceeds until nuclear densities are reached, at which point the strong nuclear force halts it abruptly, producing a rebound shock. This shock initially stalls but can be revived by energy from neutrinos streaming out of the core, ultimately driving a supernova explosion. The irony of the supernova is that the light we see, which can outshine an entire galaxy for weeks, is only a small fraction of the total energy released. the vast majority is carried away by neutrinos invisible, except to specialized detectors. Another irony is that the collapse that destroys the outer star simultaneously creates the most compact and enduring remnants in the universe: neutron stars and black holes. The third irony is that while the death of one massive star is a local catastrophe, it is also a galactic renewal, dispersing heavy elements into space, where they will seed future generations of stars and planets. The neutron star left behind after the supernova is typically only about 20 kilometers across, but contains more mass than the Sun, producing surface gravity so extreme that the escape velocity exceeds half the speed of light. Supported by neutron degeneracy pressure and possibly further by strong nuclear interactions, it is an object where matter exists in forms not found anywhere else in the universe. In some cases, the neutron star is born rotating rapidly with a magnetic field trillions of times stronger than Earth's, producing beams of radiation that sweep through space as a pulsar. In even more extreme cases, the magnetic field can reach even greater intensities, creating a magnetar whose magnetic stresses can fracture its crust, releasing bursts of high-energy radiation. If the collapsing core is more massive than about 2 to 3 solar masses, even neutron degeneracy pressure cannot halt the collapse and a black hole forms. This region of space-time is bounded by an event horizon from which nothing, not even light, can escape, and within which the known laws of physics cannot fully describe the state of matter. For the massive star, this is the final transformation, an irreversible step into a form that can persist for billions of years or more. The quiet mystery surrounding these final outcomes includes the precise boundary between neutron star and black hole formation, the role of rotation and magnetic fields in shaping the explosion, and the detailed mechanisms by which the shock wave in a supernova is revived. Observations of supernovae across different galaxies, along with gravitational wave detections from neutron star mergers, are beginning to constrain these processes, but much remains unknown. During the explosion itself, the outer layers of the star are expelled at thousands to tens of thousands of kilometers per second, colliding with surrounding material and producing a supernova remnant. The remnant expands and cools over thousands of years, its shock fronts accelerating particles to near light speed and producing synchrotron radiation observable in radio and X-ray wavelengths. The ejected material contains freshly synthesized heavy elements from the supernova nucleosynthesis, including many produced by the rapid neutron capture process, or R process, which occurs in the high neutron fluxes during the explosion. These elements, such as gold, platinum, and uranium, are dispersed into the interstellar medium, joining the chemical inventory of the galaxy. Only took millions of years of fusion to prepare a collapse measured in seconds. Only took days of silicon burning to set the stage for centuries of nebular expansion. Only took a single death to supply the seeds of countless future worlds. In the story of massive stars, brevity and intensity replace the long calm of smaller stars, yet both paths serve the same cosmic function: to turn the simplest elements into the building blocks of complexity. The end of a massive star is not a fading but a transformation, and its aftermath will continue to shape the galaxy long after the light of the explosion has gone out. When the blast of a supernova fades, what remains is a structure both ephemeral and enduring, a supernova remnant that carries the star's final message into the galaxy. The remnant expands in a complex pattern, its outer shock front ploughing into the interstellar medium, heating it to millions of Kelvin and producing X-ray emission. Behind the shock, the ejected stellar material, enriched with elements forged in the core, and during the explosion mixes gradually with the surrounding gas. Over thousands of years, the remnant's shape is sculpted by density variations in the interstellar medium, by the momentum of the ejector, and by magnetic fields that thread through both the debris and the ambient medium. The irony is that while the explosion seems instantaneous from a human perspective, the remnant it leaves evolves on timescales longer than all recorded human history, a lingering presence that outlasts the light that first marked its arrival. A second irony is that although the original star is gone, the remnant often becomes more visible than the progenitor ever was, glowing brightly in multiple wavelengths as it cools and disperses. A third irony lies in the fate of the elements themselves. Created in the most extreme environments in the universe, they eventually become part of quiet, cold clouds that seem to bear no trace of such violence. The neutron star or black hole left at the center may persist as an active engine. In the case of a neutron star, its rotation and magnetic field can generate beams of electromagnetic radiation, producing a pulsar whose regular pulses are detectable across vast distances. Some pulsars are embedded within pulsar wind nebulae, luminous bubbles powered by relativistic particles streaming from the neutron star, interacting with the surrounding ejecta and interstellar medium. In rare cases, the neutron star may be a magnetar whose magnetic field is so intense that even small shifts in its crust release immense bursts of X-rays and gamma rays. These outbursts are brief, but can be among the brightest high-energy events in the galaxy outside of supernovae themselves. Black holes, by contrast, remain unseen except by their effects on nearby matter. If they have a companion star or are embedded in dense gas, they can accrete material, producing high-energy emissions from the inner regions of the accretion disk before the material crosses the event horizon. Yet in many cases the remnant is simply a silent point in the aftermath, its presence inferred only from gravitational effects. Over time, the remnant's expanding shell slows as it sweeps up more interstellar material, eventually dissipating and merging into the background gas. The heavy elements dispersed by the explosion mix into the interstellar medium, changing its composition. The oxygen that will one day make water, the carbon that will form the basis of organic molecules, the silicon for rocks and planets, and the iron for planetary cores and future biological processes, all come from this recycling of stellar matter. Observations of the composition of young stars in different parts of the galaxy reveal the history of such enrichment, showing that successive generations of stars have progressively higher metallicities as they incorporate the products of earlier stellar deaths. The quiet mystery here lies in the exact efficiency of this mixing process. The timescales over which supernova ejecta homogenize with the surrounding medium are still uncertain, as turbulence, magnetic fields, and large-scale galactic flows all play roles. In some regions, enrichment may be rapid, producing localized pockets of high metallicity, while in others it may take hundreds of millions of years for the elements to spread evenly. In star-forming regions, supernova remnants can have both destructive and constructive effects. The shock waves can compress nearby molecular clouds, triggering the collapse of dense cores that will form new stars. Alternatively, they can disperse clouds, halting star formation locally. The interplay between these effects depends on the timing, energy, and environment of the explosion. Only took seconds for the core to collapse, yet the debris can shape the fate of nearby clouds for millions of years. Only took the light of a single star's end to seed the possibility of countless others. Only took the briefest moment in stellar time to reset the conditions for the next cycle. Over long spans, remnants fade from view, their energy spent, their material dispersed. Yet the products of their nuclear synthesis endure, joining the interstellar medium's reservoir of gas and dust. This reservoir is not static. It is stirred by galactic rotation, supernova-driven turbulence, and inflows from the intergalactic medium. Over tens to hundreds of millions of years, the enriched gas may gather again in molecular clouds, beginning the slow process of star formation anew. In this way, the life cycle of a star, particularly a massive one, becomes a cycle for the galaxy itself, maintaining the supply of heavy elements necessary for complex chemistry and eventually for life. Neutron star mergers, though rarer than supernovae, also contribute to this enrichment. When two neutron stars in a binary system lose orbital energy through gravitational wave emission, they spiral inward and eventually collide. The merger releases enormous amounts of energy and produces heavy elements through the R process, contributing significantly to the galaxy's inventory of gold, platinum, and other very heavy nuclei. These events are also sources of short gamma-ray bursts and have been directly observed through both gravitational waves and electromagnetic counterparts. The material ejected in such mergers expands and cools, forming a kilonova whose light curves reveal the synthesis of heavy elements. The irony here is that the most precious elements on Earth owe their existence to some of the rarest and most catastrophic events in the universe. Another irony is that while these mergers destroy neutron stars, they can create new black holes extending the chain of transformation. A third irony is that the gravitational waves they emit carry information about the properties of matter at nuclear densities, providing insights into physics that cannot be reproduced in any terrestrial laboratory. The remnants of supernovae and mergers alike ultimately join the interstellar medium, where they will wait in cold obscurity until gravity and time draw them into a new molecular cloud. In the grand sequence, these processes are neither beginnings nor endings, but continuations, each phase feeding the next. The galaxy becomes a patchwork of regions at different stages, some where stars are forming, others where they are dying, and still others where remnants drift invisible but essential. The quiet mystery is how these regions interact over galactic scales, balancing the competing processes of creation and destruction to sustain a steady rate of star formation over billions of years. Observations of other galaxies show that this balance can shift dramatically with bursts of star formation followed by quiescent periods. In our own Milky Way, the current rate of star formation suggests that the cycle remains in a stable self-regulating state, though it too will change over cosmic time. The path from supernova remnant to new star is long and indirect, but in the end the matter and energy released in the death of one star are part of the environment that shapes the birth of another. Only took a single lifetime of a star to write elements into the galaxy's ledger. Only took a cloud's collapse to spend those elements on new forms. Only took the silence of a remnant to prepare the noise of another ignition. In this way, the story continues without pause, though no individual star lives to see its own legacy. The material it cast into space will travel far mixed slowly, and someday, perhaps billions of years later, find itself in the heart of another collapsing core, beginning again the long steady burn of fusion that will light the darkness. In the quiet drift of interstellar space, far from the fierce compression of young clusters, cold molecular clouds begin to gather the scattered products of past generations. This is the return stage of the stellar cycle, when enriched gas and dust from planetary nebulae supernova remnants and merger ejecta blend with primordial hydrogen and helium to form new reservoirs of star-forming material. These clouds, sometimes hundreds of light-years across, are laced with filaments of higher density, where gravity will eventually take hold. Inside them, temperatures remain only a few tens of Kelvin, and molecules like carbon monoxide, ammonia, and formaldehyde trace the densest regions when observed in millimeter wavelengths. Dust grains now bearing mantles of water, ice, carbon dioxide, methane, and more complex organics act as both coolants and seeds for future solid bodies. The irony of this phase is that some of the most intricate chemistry in the galaxy takes place in its coldest, darkest environments, where visible light never penetrates. A second irony is that while gravity is the agent of collapse, it is often external disturbances like shock waves from distant supernovae or the spiral arms passage that provide the push needed to overcome internal support. The third irony is that the material here destined to become luminous stars spends most of its time invisible, betraying its presence only in the faint emission lines of cold molecules. As regions within these clouds collapse, they fragment into many cores, each with its own potential future. The mass distribution of these cores, known as the core mass function, resembles the initial mass function of stars, suggesting a direct connection between the two, though the details of this mapping are still uncertain. Magnetic fields thread the clouds, influencing the shape of the filaments and resisting collapse until ambipolar diffusion allows neutral particles to drift past charged ones, gradually reducing magnetic support. Turbulence injected by previous generations of stellar feedback stirs the gas and creates a network of density contrasts, some of which will collapse, while others dissipate. The quiet mystery here is how these competing influences, gravity turbulence, magnetic pressure, and thermal pressure combine to set the efficiency of star formation. Observations show that only a few % of a cloud's mass ends up in stars before feedback disperses the rest, but the reasons for this low efficiency remain a topic of active research. Over hundreds of thousands to millions of years, the densest cores become opaque to their own radiation, heating internally as gravitational energy converts to thermal energy. In these protostellar objects, accretion disks form as angular momentum prevents direct infall. Jets and outflows emerge along the poles powered by magnetic processes and accretion energy clearing cavities through which radiation escapes. The material in the disks may begin to coagulate into planetesimals, though in many cases the dynamics of accretion and migration will prevent long-term survival. For the star itself, the early stages are dominated by contraction and heating, moving down pre-main sequence tracks on the Hertzsprung-Russell diagram until core temperatures are high enough for hydrogen fusion to begin. The irony is that while each star's formation is a singular event, the processes involved are nearly universal, repeating across the galaxy, and observable at multiple stages in regions like the Orion Nebula, the Carina Nebula, and the dense star-forming knots in other galaxies. Another irony is that the surrounding environment shaped by past stellar deaths often determines whether a star will have a chance to form at all, making each generation both the product and the parent of the next. The third irony is that while the basic physics of collapse and fusion ignition are well understood, the initial conditions are so varied that no two stars emerge exactly alike. In clusters, massive stars form first and begin to influence their surroundings almost immediately. Their intense ultraviolet radiation ionizes nearby gas, creating expanding H2 regions that can compress adjacent molecular material or evaporate it away. Stellar winds from these massive stars sweep up shells of gas, sometimes triggering new star formation in a process known as triggered collapse. Eventually, the most massive stars will explode as supernova, injecting fresh energy and material into the cloud, potentially halting star formation in some areas while initiating it in others. Over tens of millions of years, the original molecular cloud is dispersed, its material either locked into stars and planets or returned to the interstellar medium for another cycle. The quiet mystery in this interplay is the balance between constructive and destructive feedback, why some regions of the galaxy maintain steady star formation, while others undergo bursts followed by long quiescent periods. The enrichment of the interstellar medium continues through smaller-scale processes as well. Winds from asymptotic giant branch stars carry carbon, nitrogen, and dust into the surroundings. Binary interactions, including mass transfer and mergers, produce novae and type Ia supernovae that contribute ion peak elements. Cosmic rays accelerated in supernova shocks permeate molecular clouds and drive chemical reactions that would otherwise proceed too slowly in the cold. Each of these inputs is a subtle thread in the larger tapestry of galactic evolution. Over hundreds of millions of years, spiral density waves in galaxies like the Milky Way sweep through the disk, compressing gas and organizing star formation into spiral arms. Within these arms, star-forming regions shine in the infrared as embedded clusters heat the surrounding dust. Beyond them, older stellar populations dominate their light redder and steadier. The movement of stars and gas through the galaxy continually reshapes the distribution of material, mixing the contributions of many generations. Only took the death of one star to see the birth of another. Only took the slow drift of dust grains to prepare the foundation for worlds. Only took the cooling of hot debris into cold shadow to begin the cycle again. In this endless exchange, the galaxy maintains a delicate equilibrium with gas consumption, balanced by replenishment from stellar feedback, infall from the intergalactic medium, and mergers with smaller galaxies. Over cosmic time, this balance will shift. Galaxies consume their gas and eventually transition to quiescence. But for now, in the present moment of the Milky Way, the cycle continues, weaving together the fates of stars across vast distances and timescales. The path from enriched gas to molecular cloud to collapsing core is the beginning of a star's life, yet it is also the final chapter of the stars that came before. In this way, the life cycle of a star is never truly isolated. It is a single loop in a chain that stretches back to the first stars in the universe, whose supernova seeded the cosmos with the first heavy elements. The quiet mystery is how many such cycles it will take before the galaxy's capacity to form stars wanes, and what kinds of stars and planets will exist in those distant times. For now, the dust continues to drift, the gas continues to cool, and gravity continues its patient work setting the stage for the ignition of new light in the dark. In the early life of a newly formed star cluster, the diversity of stellar masses becomes immediately apparent in the way each star evolves. The most massive begin to leave the main sequence almost at once, swelling into giants or supergiants within a few million years, while smaller stars remain in their steady hydrogen-burning phase for billions. The cluster itself remains gravitationally bound only if the total stellar mass exceeds the disruptive influence of stellar winds, radiation pressure, and supernovae from the most massive members. These energetic processes clear out the residual gas left over from star formation, altering the gravitational potential, and in many cases causing the cluster to expand and lose stars. The irony is that the very stars that light the cluster most brilliantly are also those most likely to dissolve it, their winds and explosions unbinding the less massive members. A second irony is that while clusters are cradles for stars, most stars in the galaxy, including the Sun, will spend the vast majority of their lives wandering alone after leaving these birthplaces. The third irony is that a star's mass at birth, fixed in the first moments of its formation, determines nearly every major stage of its life, yet this decisive quantity depends on initial conditions that are still not fully understood. In open clusters, which are relatively loose and young, the variety of stellar colours along the main sequence is evident, and the turn-off point on the Hertzsprung-Russell diagram marks the age of the cluster. In globular clusters which are far older and more tightly bound, all massive stars have long since died, leaving only low-mass stars and the remnants of earlier generations. The composition of stars in these clusters provides a record of the chemical enrichment of the galaxy at the time of their formation, with older clusters showing lower metallicities. The quiet mystery here lies in the formation of multiple stellar populations within some clusters with distinct chemical signatures that suggest episodes of star formation separated by millions of years, challenging the view of clusters as products of a single burst. Within individual stars, life on the main sequence is stable but not static. In solar-type stars, rotation slows over time due to magnetic braking, reducing magnetic activity, and the frequency of flares and star spots. The luminosity gradually increases as helium ash accumulates in the core, and the hydrogen-burning shell becomes more active. For low-mass stars below about 0.4 solar masses, the story is even slower. These fully convective stars mix hydrogen throughout their interiors, allowing them to burn nearly all of it, and prolonging their main sequence lifetimes to tens or even hundreds of billions of years, far longer than the current age of the universe. This is one of the great ironies of stellar evolution. The smallest stars live the longest, yet none have yet completed their life cycle since the universe began. Another irony is that these faint red dwarfs, though they are the most common stars in the galaxy, are almost invisible to the naked eye from Earth, contributing little to the night sky's brightness despite their abundance. A third irony is that because of their slow pace, their eventual fates are among the least observed and most theoretically modelled, existing, for now, only in calculations. Stars of intermediate mass between about 2 and 8 solar masses evolve more quickly and spend less time on the main sequence. They ignite helium smoothly after leaving the main sequence, pass through horizontal branch or blue loop phases, and then ascend the asymptotic giant branch before ending as white dwarfs surrounded by planetary nebulae. White dwarfs themselves cool on timescales so long that no star in the universe has yet cooled to the background temperature of space, meaning that black dwarfs' cold inert remnants remain purely theoretical for now. The quiet mystery here concerns the crystallization of white dwarf interiors, a process predicted to occur as they cool and the carbon-oxygen mixture solidifies. Observations of white dwarf cooling sequences in clusters suggest that this crystallization indeed happens, releasing latent heat and slowing the cooling rate, but the details of the process and its dependence on composition remain under study. In binary systems, stellar evolution can follow different paths. Mass transfer between stars can strip away outer layers, expose stellar cores, and even lead to mergers that produce unusually massive stars or trigger explosive events. Type Ia supernovae, for example, occur when a white dwarf in a close binary accretes matter from its companion until it approaches the Chandrasekhar limit, causing runaway carbon fusion throughout the star. These explosions are critical for enriching galaxies with iron peak elements and serve as standard candles for measuring cosmic distances. Yet their progenitor systems remain a quiet mystery, with debates over whether the dominant channel involves accretion from a normal star, the single degenerate scenario, or the merger of two white dwarfs, the double degenerate scenario. In more massive binaries, interactions can produce X-ray binaries, where a neutron star or black hole accretes matter from its companion, emitting intense X-rays from the hot inner regions of the accretion disk. Some of these systems launch relativistic jets, beams of plasma moving at nearly the speed of light, whose formation mechanisms are still not fully understood. In rare cases, massive stars in binaries may merge before either has ended its life, creating a single star more massive than either progenitor and altering its evolutionary path. These interactions complicate the picture of stellar evolution, but they are common enough that a significant fraction of massive stars are thought to experience them. Only took the gravity of two stars to rewrite both their destinies. Only took a shared orbit to trigger an explosion visible across the universe. Only took a chance encounter in a crowded cluster to change the path set at birth. Across all these variations, the fundamental principles remain. Mass determines the internal pressures and temperatures that govern nuclear fusion. Fusion determines the balance between gravity and radiation pressure, and that balance shapes the star's structure and lifetime. The environments in which stars form, whether solitary or in clusters in metal-poor or metal-rich regions, and with or without close companions, add layers of complexity to these basic rules. The quiet mystery that runs through all of stellar evolution is how these variables combine to produce the immense diversity of stars observed in the universe, from the smallest red dwarfs to the most massive luminous blue variables, from isolated white dwarfs to dense clusters of neutron stars in the cores of globular clusters. The patterns are clear in broad strokes, yet the details remain elusive, and each observation of a new or unusual star has the potential to refine the theory. In the long view, every star, regardless of its mass or path, is a temporary arrangement of matter and energy, a luminous phase in the ongoing transformation of the galaxy's raw material. The end of that phase, whether in quiet cooling or explosive dispersal, feeds into the cycle that ensures there will always be new stars, at least for as long as the galaxy retains its reservoirs of gas and dust. The link between generations is unbroken, though the individual lifetimes and endings vary widely. Only took a single rule, gravity's pull balanced by fusion's push, to produce every variety of stellar life. Only took the same elements arranged differently to fill the sky with such difference. Only took the briefest cosmic moment for any one star to live, yet together they make the galaxy seem eternal. The white dwarf stage is a coda of stillness compared to the fusion-driven dynamism that preceded it. With no nuclear reactions in its interior, a white dwarf shines only by the release of residual thermal energy stored in its dense degenerate matter. Composed mostly of carbon and oxygen in the case of stars that began with up to about 8 solar masses, it is supported entirely by electron degeneracy pressure, which does not depend on temperature. This means that as the white dwarf radiates away heat, it does not contract further but simply cools and fades. The surface temperature can initially exceed 100,000 Kelvin, producing a brilliant ultraviolet glow, but over billions of years it falls toward just a few thousand Kelvin, shifting the emission into the red and infrared. The irony is that although the white dwarf is one of the densest objects in the universe, with a mass comparable to the Sun packed into a sphere about the size of Earth, it is among the most structurally stable, destined to persist for trillions of years if undisturbed. A second irony is that the smallest stars, which will eventually become the faintest white dwarfs, are the ones that will last longest in this phase, so the faintest will outlive the brightest. The third irony is that even as they fade into near invisibility, white dwarfs can remain dangerous in the right circumstances. If part of a close binary, they can accrete matter and ignite in nova eruptions, or even explode as type Ia supernovae. The cooling of a white dwarf is a slow, predictable process governed by the loss of heat through its thin outer atmosphere. As it cools, crystallization can occur in the interior, when the ions in the carbon-oxygen plasma arrange themselves into a solid lattice. This process releases latent heat, slowing the cooling rate for a time, and producing a subtle kink in the white dwarf luminosity function observable in star clusters. The crystallization front moves outward from the center, and in the most massive white dwarfs, it may occur earlier due to higher interior pressures. Eventually, if the universe lasts long enough, all white dwarfs will cool to become black dwarfs, cold, dark spheres that no longer radiate appreciable energy. However, the timescale for this is longer than the current age of the universe, by many orders of magnitude, so no black dwarfs exist yet. The quiet mystery in this stage lies in the precise thermal conductivity of degenerate matter and the influence of trace elements like neon on the cooling rate. Small differences in these properties can lead to significant changes in the predicted ages of stellar populations when white dwarf cooling is used as a chronometer. White dwarfs with helium cores also exist typically, the remnants of stars whose evolution was truncated by mass loss in binary systems before helium ignition. These are less massive, often less than half a solar mass, and larger in radius for the same degeneracy pressure, and they cool differently from their carbon-oxygen counterparts. At the other extreme, the most massive white dwarfs can have oxygen neon magnesium cores, the product of more massive progenitors that lost their envelopes before core collapse. In binaries, accretion onto a white dwarf from a companion star can lead to a range of phenomena. If the accreted hydrogen builds up on the surface and ignites in a thermonuclear runaway, the result is a nova, a sudden brightening that can repeat as the process cycles. If the accretion rate is high enough, and the white dwarf's mass approaches the Chandrasekhar limit, the entire star can ignite in a runaway carbon fusion event, disrupting it completely as a Type Ia supernova. These explosions are critical for measuring cosmic distances because their peak luminosities are consistent enough to serve as standard candles. Yet the exact nature of the progenitor systems remains uncertain, with evidence supporting multiple channels. Outside of binaries, isolated white dwarfs evolve quietly, their luminosity and temperature declining steadily. The youngest and hottest are often found in planetary nebulae ionizing the surrounding gas, but as the nebula disperses, the white dwarf stands alone. Over time, interactions with other stars or the galactic potential can move it far from its birthplace. The space velocity of white dwarfs reflects the motions they inherited from their progenitor stars and any kicks received during binary interactions. Only took a fraction of a solar mass in electrons to hold up the remnant of a giant. Only took the cooling of dense matter to turn the brightest ember into a fading cinder. Only took a single limit in mass to decide whether the end would be silent or explosive. In the long-term view of the galaxy, white dwarfs are its enduring population surviving long after their more massive counterparts have gone supernova. They are also the future of most stars now shining, including the Sun. In about 5 billion years, the Sun will exhaust the hydrogen in its core, expand into a red giant, shed its outer layers, and leave behind a white dwarf of about half its present mass. That remnant will slowly cool, perhaps forming crystals deep inside as the planets either drift away or become cold airless rocks orbiting an ever dimmer light. The quiet mystery that surrounds this fate is less about the physics, which is well understood, and more about the long-term evolution of such remnants in a changing universe. Over trillions of years, gravitational interactions could eject many white dwarfs from the galaxy into intergalactic space. Those that remain will grow colder and darker as the cosmic background temperature falls. The deep future of white dwarfs lies beyond direct observation, but they remain key markers of stellar history. In globular clusters, their cooling sequences provide age estimates that anchor our understanding of galactic formation. In the local neighborhood, surveys of white dwarfs reveal the distribution of stellar remnants and the star formation history of the Milky Way over the last 10 billion years. They are silent archives of nuclear burning long past their compositions and masses recording the processes that shaped them. Only took a single star's lifetime to create a remnant that will outlast the galaxy's spiral arms. Only took a few billion years of fusion to set the stage for trillions of years of cooling. Only took the quiet end of one star to leave a mark on cosmic time that will fade only when the universe itself grows cold. For stars that end not as white dwarfs but as neutron stars, the closer fusion in the core leads not to a gradual cooling, but to a collapse so sudden that the densities reached surpass anything outside the realm of atomic nuclei. A neutron star forms when the collapsing iron core of a massive star is halted by neutron degeneracy pressure, a quantum mechanical effect that arises because neutrons, like electrons, cannot occupy the same state. The result is an object with a mass typically between about 1 and 2 solar masses packed into a sphere roughly 20 kilometers in diameter. The surface gravity is enormous, about 200 billion times that of Earth, and the escape velocity is close to half the speed of light. The interior structure is layered a thin atmosphere of plasma above a crust of nuclei and electrons, which becomes increasingly neutron-rich with depth, until the nuclei dissolve into a fluid of neutrons, protons and electrons in the core. Deeper still, at extreme densities, exotic states of matter may occur such as hyperons, meson condensates or deconfined quark matter, though the exact composition remains one of the quiet mysteries of astrophysics. The neutron star is born hot with temperatures exceeding 10 billion Kelvin, but it cools rapidly through the emission of neutrinos' invisible particles that escape freely from its interior. Within a few years, the temperature drops to millions of Kelvin, and the surface emits primarily in X-rays. If the neutron star retains a strong magnetic field, often trillions of times stronger than Earth's, and rotates rapidly, it can become a pulsar emitting beams of radio waves, X-rays or gamma rays from its magnetic poles. As the star spins, these beams sweep across space, and if aligned with Earth, they produce pulses with extraordinary regularity. The irony is that this precise timing, rivaling the best atomic clocks, comes from one of the most violent and chaotic events in the universe, the collapse of a massive star's core. A second irony is that the neutron star's small size and immense density make it incredibly stable against further collapse, yet a slight increase in mass, perhaps from accretion, can push it past the threshold into a black hole. The third irony is that while they are born in brilliant explosions, most neutron stars quickly fade from view, unless they are active pulsars or accreting matter from a companion. In binary systems, neutron stars can accrete matter from a companion star, forming an accretion disk that radiates strongly in X-rays as material spirals inward and heats to millions of Kelvin. Such systems, known as X-ray binaries, can be persistent or transient depending on the mass transfer rate. In some cases, the accreted material accumulates on the neutron star's surface until it ignites in a thermonuclear burst, producing a sudden increase in X-ray brightness, lasting seconds to minutes. These X-ray bursts are among the most luminous events in the galaxy in their energy range, and they provide valuable insights into the physics of dense matter and nuclear reactions under extreme gravity. Over time, the neutron star's rotation slows as it loses energy through electromagnetic radiation and particle winds. The rate of slowdown depends on the strength of its magnetic field, and in millisecond pulses, neutron stars spun up to hundreds of rotations per second by accreting matter from a companion. The slowdown is so gradual that they can remain detectable for billions of years. The quiet mystery surrounding neutron stars extends to the equation of state that describes matter at nuclear densities. Observations of neutron star masses and radii, particularly through X-ray pulse profiles, and gravitational wave signals from neutron star mergers are helping to constrain this equation, but the exact behavior of matter under such extreme conditions is still not fully known. When two neutron stars in a binary merge, the result can be a more massive neutron star, or a black hole, accompanied by the ejection of neutron-rich material that undergoes rapid neutron capture to form heavy elements. These mergers produce both gravitational waves and electromagnetic signals, as seen in the kilonova event detected in 2017, confirming that they are a significant source of elements like gold and platinum. The irony of these mergers is that they are both an end and a beginning, the destruction of two neutron stars and the creation of a flood of new matter for the galaxy. Another irony is that the gravitational wave signal, a tiny ripple in space-time, carries the imprint of the final moments of the merger across hundreds of millions of light years, while the light from the event tells of the heavy elements forged in its aftermath. The third irony is that such rare events can have outsized impacts on the chemical evolution of a galaxy, influencing the makeup of planets and even life. Neutron stars can also exist in more quiescent states as cooling isolated objects that emit primarily in thermal X-rays. Some are found near the centers of supernova remnants still embedded in the expanding debris of their birth. Others have moved far from their birthplaces propelled by kicks received during the supernova that reached hundreds of kilometers per second. These high velocities can carry neutron stars into the halo of the galaxy, or even eject them entirely into intergalactic space. Over billions of years, an isolated neutron star will cool to the point where it is no longer detectable, except through its gravitational influence. Only took the collapse of a massive star to compress matter beyond the reach of chemical bonds. Only took a few seconds of infall to create an object that can outlast entire galaxies. Only took the brief flash of a supernova to hide a remnant that may shine invisibly for eons. In the grand cycle of stellar life, neutron stars occupy a narrow but profound branch of the evolutionary tree. They represent a state of matter so dense and unfamiliar that studying them pushes the limits of physics, yet they are also integral to the galaxy's chemical and dynamical history. Whether as pulsars, X-ray binaries, magnetars, or quiet wanderers, they are the enduring witnesses of stellar death, each carrying in its structure the imprint of the processes that formed it. The quiet mystery is how many remain undiscovered, drifting unseen in the vastness their existence betrayed, only when they pass through a beam of gas, a magnetic alignment, or the final embrace of another neutron star. In the silence of interstellar space they wait unchanged in their essential structure, until the next transformation calls them into a new role in the universe's unfolding story. For the most massive stars, those whose collapsing cores exceed the maximum mass that neutron degeneracy pressure can support, the final transformation is into a black hole, a region where gravity curves space-time so completely that nothing, not even light, can escape once it crosses the event horizon. The formation occurs when the collapsing core, already beyond nuclear density, has no force left to resist its inward fall, and the infall continues unchecked until the matter is compressed into a volume so small that our current physics cannot fully describe it. The surrounding layers, if not entirely blown away by the initial shock of the supernova, may fall back into the new black hole, increasing its mass. The irony is that while the black hole's presence can profoundly affect its surroundings, it cannot be seen directly. Only its influence on nearby matter and light reveals its existence. A second irony is that the singularity at its center is hidden forever behind the event horizon, a surface that marks the limit of causal contact with the rest of the universe. The third irony is that the simplest description of a black hole, defined only by its mass, spin and charge, conceals the extraordinarily complex history of the star and environment that formed it. If the black hole is part of a binary system, it can accrete gas from a companion, forming an accretion disk that heats to millions of Kelvin as matter spirals inward. This disk emits strongly in X-rays and sometimes produces jets of relativistic plasma that extend for light years, their origin linked to magnetic fields twisted by the black hole's rotation. These systems, known as X-ray binaries when the accretor is a stellar mass black hole, are valuable laboratories for testing theories of accretion physics, jet formation, and the effects of strong gravity on light and matter. The quiet mystery here lies in the details of how the accretion disk's magnetic and turbulent processes convert gravitational energy into the ordered structures of jets, a mechanism still not fully resolved despite decades of observation and simulation. Stellar mass black holes in binaries can also reveal themselves through gravitational waves when they merge. The detection of such events by gravitational wave observatories has opened a new window into stellar evolution, showing that black holes with masses exceeding those expected from conventional supernova models do exist, possibly formed through direct collapse without an explosive ejection of the outer layers. The irony is that while gravitational waves carry no image and no light, they can tell us the masses and spins of the merging black holes with remarkable precision, offering clues to their origins. Another irony is that these mergers, entirely invisible in electromagnetic light, unless accompanied by matter, can still shake the fabric of space-time across billions of light-years, briefly altering the length of every meter on Earth by a fraction smaller than a proton's diameter. The third irony is that the same gravity that once bound stars together can in these events send ripples through the universe itself, making space and time dynamic participants in stellar endings. In isolation, a black hole will slowly drift through the galaxy, its gravity influencing the orbits of nearby stars and gas, but otherwise leaving little trace. If it passes through a dense region, it may capture gas that emits radiation as it falls inward, but most will remain silent undetected except by its gravitational effects. Over cosmic timescales, stellar mass black holes may wander far from their birthplaces, their distribution tracing the history of massive star formation and death. The quiet mystery is how many such black holes populate the Milky Way. Estimates suggest millions, but only a small fraction have been detected through their interactions with other objects. In the dense cores of star clusters, interactions between stars and remnants can produce black hole binaries that may merge within the cluster or be ejected into interstellar space. Some theories suggest that repeated mergers in such environments could form intermediate mass black holes, bridging the gap between stellar mass and supermassive black holes found in galactic centers. Observational evidence for intermediate mass black holes is still limited, but candidates exist often identified by unusually luminous X-ray sources or the dynamics of stars in dense clusters. The eventual fate of stellar mass black holes in the deep future is even more extreme in its stillness than that of white dwarfs or neutron stars. Without a companion or nearby gas, they emit no light, and lose mass only through Hawking radiation, a quantum mechanical process predicted to cause black holes to evaporate over timescales vastly longer than the current age of the universe. For a stellar mass black hole, this timescale is on the order of 1067 years, making them among the most enduring structures in the cosmos. Only took a few seconds of collapse to create an object that will outlast galaxies, stars, and even the current era of starlight. Only took the death of a star to produce a remnant so final that time itself seems irrelevant to its existence. Only took the smallest observable feature's mass spin charge to contain the entire complexity of its birth and fate. The environments around black holes can be surprisingly dynamic despite the stillness of the central object. In galaxies with active star formation, black hole binaries can form and merge within a few million years, producing gravitational wave events that add to the background hum in space-time. In older stellar populations, mergers may occur after billions of years of slow orbital decay, their gravitational waves arriving long after the galaxies and clusters that hosted their progenitors have changed beyond recognition. The study of these mergers connects the life cycles of individual stars to the evolution of entire galaxies, linking processes across scales that span light years to billions of light years. The quiet mystery of black holes is not only in their interiors forever hidden, but in the histories of the stars that become them. Understanding the conditions that lead to direct collapse, the effects of metallicity on mass loss, and the role of binary evolution in producing heavy black holes are central questions in astrophysics. Observations of black holes in different environments combined with simulations continue to refine these answers, but the diversity of outcomes remains large. In the full context of stellar evolution, black holes mark one of the ultimate endpoints, along with white dwarfs and neutron stars, but they also feed the next stages in subtle ways. A black hole's gravitational influence can shape the structure of a cluster, and mergers inject energy into their surroundings. In rare cases, the tidal disruption of a passing star can feed a dormant black hole, producing a flare of radiation that briefly announces its presence. These events, while catastrophic for the star, return its elements to the interstellar medium, connecting even this most final of remnants to the continuing cycle of matter. In the darkness beyond the reach of light, black holes drift with a permanence unmatched by any other stellar product, each a silent monument to the mass, energy and gravity that shaped it. They are both absence and presence, their invisibility, a statement of their completeness. In time's scale so vast they dissolve the meaning of beginning and end, they will remain when other remnants have cooled, when stars no longer form, and when the universe has grown cold and dim. Across the galaxy, the interplay of all stellar endings, white dwarfs, neutron stars and black holes writes a layered record of past generations. Each remnant type shapes its surroundings differently, yet together they form the skeletal framework of galactic evolution. White dwarfs in their abundance mark the quiet conclusion of low and intermediate mass stars cooling slowly while orbiting the galaxy like ancient embers. Neutron stars, rarer but more exotic, carry the imprint of high-density physics and often leave visible signatures as pulsars or magnetars. Black holes, the most secretive, vanish into the background unless paired with matter to consume or another black hole to merge with. The irony is that the most common remnants are the most observable, while the rarest often remain hidden, yet the rare events tied to them, novae supernova mergers, are some of the most luminous and far-reaching in their consequences. A second irony is that the galaxy's chemical evolution depends disproportionately on the short-lived massive stars whose remnants are few in number. A third irony lies in the fact that every one of these stellar corpses, regardless of type, began as a cloud of diffuse gas, its fate sealed by mass and conditions at birth. In star-forming regions, these remnants are seldom alone in their influence. The dispersal of molecular clouds by ultraviolet radiation winds and explosions from earlier generations changes the density structure of the surrounding gas. Shockwaves from supernovae compress nearby material, possibly triggering collapse in dense clumps, while winds from asymptotic giant branch stars enrich the same gas with carbon and heavy elements from the S process. The feedback is neither purely constructive nor purely destructive. It is an intricate balance that shifts depending on timing, distance, and environment. The quiet mystery here is how these competing effects average out over galactic scales to produce the relatively steady star formation rate observed in galaxies like the Milky Way. In young stellar clusters, the remnants of massive stars can still be found within the same gravitationally bound system as their low-mass siblings, at least until dynamical interactions eject them. Encounters in dense environments can alter orbits, swap companions in binaries, and even send neutron stars or black holes hurtling out of the cluster at high speeds. These ejected remnants become wanderers travelling through the galactic halo or disk, occasionally passing near other stars but rarely interacting strongly. The irony is that such high-speed travellers can carry the chemical signature of their birth cluster, far from its original location, contributing to the mixing of stellar populations across the galaxy. Over longer spans, the remnants themselves begin to interact less with their surroundings, becoming part of the galaxy's dynamically hot components, populations with high-velocity dispersions and little remaining correlation to their points of origin. In the galactic disk, remnants orbit in the same general plane as the stars, while in the halo, they follow more eccentric and inclined paths. The distribution of remnants in the halo preserves clues about the galaxy's merger history, as some originated in dwarf galaxies that were later accreted. The quiet mystery here lies in identifying these remnants and tracing their origins, a task made difficult by their faintness and the vastness of the galaxy. Chemical tagging, in which the abundances of multiple elements are measured to link stars to their birth environments, may one day extend to certain white dwarfs and neutron stars with discernible surface compositions. Over cosmic timescales, the accumulation of remnants gradually alters the galaxy's baryonic mass distribution. While the light from living stars dominates the visible appearance of a galaxy, the mass locked in remnants can be significant, particularly in older populations. White dwarfs make up a large fraction of this hidden mass, their dim light contributing only marginally to the galaxy's luminosity. Neutron stars and black holes, though much less numerous, also add to the non-luminous mass. The irony is that this growing population of remnants is a byproduct of star formation, yet it plays little direct role in sustaining it except indirectly through gravitational effects and occasional interactions. In regions with high stellar densities such as the cores of globular clusters, remnants can dominate the local mass budget, affecting the cluster's evolution. In some clusters, mass segregation causes heavier objects like neutron stars and black holes to sink toward the center, where they may form binaries that release enough energy through interactions to hold the cluster against collapse. Such binaries can eventually merge, producing gravitational waves. The quiet mystery here is whether clusters can retain black holes over billions of years, or whether most are ejected through dynamical interactions. Simulations and observations suggest both outcomes are possible, depending on the cluster's initial conditions and subsequent encounters. Beyond the scale of individual clusters and galaxies, the cumulative effect of all stellar deaths in the universe shapes the intergalactic medium. Outflows from galaxies powered partly by supernova-driven winds carry metals into intergalactic space, enriching even regions far from any galaxy. This material may later be reaccreted, fueling new rounds of star formation, or remain in diffuse form for billions of years. The irony is that while stellar evolution is often framed as an internal galactic process, its reach extends well beyond a galaxy's visible bounds. Another irony is that the oldest known stars found in the galactic halo formed from gas that was enriched by only a few supernovae, yet their compositions preserve that ancient chemical fingerprint billions of years later. A third irony is that the vast structures traced by the intergalactic medium on cosmic scales are partly built from atoms forged in the brief lifetimes of massive stars. As time advances, the balance of the stellar population shifts toward longer-lived lower-mass stars. Massive star formation declines as gas supplies dwindle and the frequency of core collapse supernovae decreases. White dwarfs accumulate steadily, while the rate of new neutron star and black hole formation slows. The galaxy grows redder and fainter, entering a phase dominated by slow stellar evolution rather than rapid turnover. The quiet mystery for this future is how long the galaxy can sustain any star formation at all, and how its final population mix of remnants will compare to what is seen today. Only took a few generations of massive stars to enrich the galaxy's gas to its current metallicity. Only took the life cycles of billions of low-mass stars to fill the disk with a steady glow. Only took the combined mass of countless remnants to build a hidden structure that outlasts most of the light we see. In the story of the galaxy, the life cycle of a star is never an isolated tale. It is one voice in a chorus that spans billions of years and hundreds of billions of stars, each contributing in its own way to the evolving harmony of matter, energy, and gravity. The remnants, silent and persistent, carry forward the memory of that song long after the light that sang it has gone out. The continuity of the stellar cycle depends not only on the lives and deaths of individual stars, but on the slow choreography of galaxies themselves. For it is the large-scale flow of gas that determines how many new stars can be born from the ashes of the old. Spiral galaxies like the Milky Way maintain their star-forming capacity by drawing on reservoirs of interstellar gas, some recycled from stellar winds, and supernova some accreted from the intergalactic medium. This gas must cool, condense, and become molecular before gravity can gather it into clouds dense enough to collapse. The irony is that the same feedback processes that enrich the gas with heavy elements and dust also heat and stir it, delaying its return to star-forming conditions. A second irony is that star formation is most efficient in regions already rich in heavy elements, yet those same metals come only from previous generations of stars, creating a dependence between past and future. The third irony lies in the fact that while galaxies appear stable over millions of years, their star formation rates fluctuate on shorter timescales in response to the interplay of inflow-outflow and internal dynamics. In the Milky Way, molecular clouds form along spiral arms where density waves compress the gas. Within these clouds, the processes already traced through the birth of a star repeat endlessly: fragmentation, core collapse, disk formation, and ignition. Yet each new generation of stars forms in a subtly altered chemical environment compared to the one before. The earliest generations contained almost no elements heavier than helium, while present-day stars form from material enriched by billions of years of nucleosynthesis. This steady enrichment influences everything from stellar opacity to planet formation, shaping the diversity of systems observed today. The quiet mystery is how variations in metallicity across space and time influence the types of stars that form, particularly the distribution of masses and the prevalence of massive stars whose short lives drive further enrichment. In galaxy centers, the conditions can be extreme. High gas densities and turbulent motions lead to intense bursts of star formation, sometimes producing superstar clusters that contain millions of stars within a few light years. Here, stellar evolution proceeds under crowded conditions with frequent interactions and higher chances for binary formation and mergers. Massive stars in these environments may evolve differently, losing mass more rapidly due to stronger winds or colliding with companions before they can reach their natural end states. The irony is that while such regions are among the most efficient in converting gas into stars, the intense feedback from those stars can quickly halt further formation by expelling gas from the region. Beyond the visible disk in the galaxy's halo, remnants from long-past mergers with dwarf galaxies drift among older stars. Some of these remnants are white dwarfs, neutron stars, and black holes, their origins traceable to small galaxies absorbed billions of years ago. Their motions preserve information about those ancient events, even when the structures of the original galaxies have long since dissolved. The quiet mystery here lies in unraveling this fossil record, piecing together the orbits and compositions of halo stars and remnants to reconstruct the Milky Way's assembly history. Interactions between galaxies can profoundly reshape star formation. When galaxies pass near each other or collide, tidal forces compress gas and trigger starbursts, brief but intense episodes of star formation. These events can produce entire generations of massive stars whose rapid evolution and explosive deaths enrich the surrounding medium on short timescales. The irony is that while such interactions are often destructive to galactic structure, they can be highly creative in terms of stellar production. A second irony is that the most spectacular starbursts may exhaust their fuel quickly, leading to a subsequent lull in star formation. A third irony is that in the most extreme cases, feedback from these bursts can drive gas entirely out of a galaxy, quenching future formation for billions of years. Over longer spans, galaxies evolve from active blue star-forming systems into quiescent red ones, as their gas is depleted or heated beyond the point where it can cool effectively. In this future state, the population becomes dominated by long-lived low-mass stars and the growing number of remnants. The galaxy's light dims and its appearance changes, but the remnants persist, orbiting silently as the luminous population dwindles. The quiet mystery is how long galaxies like the Milky Way can sustain significant star formation before transitioning to quiescence, and whether this change is driven more by internal processes or by the environment within galaxy groups and clusters. On cosmic scales, the star formation rate density of the universe peaked about 10 billion years ago and has been declining since. This decline reflects the gradual exhaustion of cold gas and the heating of the intergalactic medium by feedback from galaxies and active galactic nuclei. Yet even in this lower activity era, the cycle of stellar birth and death continues everywhere that gas remains available. Each new star adds to the diversity of the stellar population, and each death returns enriched material to the medium, keeping the cycle in motion, though at a slower pace than in the universe's youth. Only took the merger of gas-rich galaxies to light up entire clusters with new stars. Only took the spiral arm's compression to seed thousands of suns. Only took the passage of a tidal shock to turn diffuse gas into a glowing nursery. In this grand flow, the fate of individual stars is both deeply personal to their own mass and chemical makeup, and yet entirely subordinate to the wider circulation of matter through galaxies. The connection between scales is constant. The light of a single supernova can alter the chemistry of a molecular cloud dozens of light years away. The slow enrichment of an entire galaxy over billions of years can determine the types of planets that form around small stars. The quiet mystery remains how finely tuned these processes must be for galaxies to sustain habitable environments for long spans, and whether this balance is common or rare in the cosmos. As the Milky Way continues its slow orbit through the local group, its future will be shaped by its encounter with the Andromeda Galaxy in about 4 billion years. This collision will trigger waves of star formation as gas is compressed, perhaps creating new generations of massive clusters. In the aftermath, the galaxies will merge into a single larger system, likely with reduced star formation once the gas is consumed or expelled. The remnants existing, then white dwarfs, neutron stars, black holes, will mingle with those from Andromeda, blending the histories of two stellar populations. Only took a single galactic encounter to mix billions of years of separate stellar stories. Only took the motions of dark matter halos to set the stage for a collision written since the universe's youth. Only took the slow inevitability of gravity to bind two vast cities of stars into one. In the end, whether in isolated regions of ongoing star formation or in the merged hearts of galaxies, the life cycle of a star plays out against the same backdrop matter, gathered, fused, dispersed, and gathered again, carrying forward the chemical and energetic legacy of every generation before. The galaxy is both the stage and the product of this ongoing drama, and the stars in their billions are the actors whose roles vary, but whose shared story never truly ends. In the far future, when the galaxy's great clouds have thinned and cooled to the point where new stars are rare, the remnants of past generations will dominate the stellar landscape. The bright, short-lived giants will be gone, their ashes scattered into interstellar space, and long since blended into a diffuse haze of gas and dust. What remains will be the slow glow of red dwarfs, the faint embers of white dwarfs, the invisible mass of neutron stars and black holes, and the faint arcs of stellar streams tracing ancient gravitational tides. The irony is that the most enduring members of this population will be the smallest and faintest, their light, almost imperceptible, yet their numbers vast enough to keep the galaxy speckled with points of warmth for trillions of years. A second irony is that the luminous giants that once defined the galaxy's appearance will have left almost no direct trace except in the chemical makeup of later generations. The third irony is that while the remnants will preserve the memory of the galaxy's star-forming past, they will also signal its approaching stillness. Red dwarfs with masses less than half that of the Sun will continue to fuse hydrogen for hundreds of billions of years, their convection keeping their interiors mixed and efficient. These stars will evolve so slowly that in the current age of the universe, none have yet left the main sequence. Around them, planets may remain habitable for epochs far longer than the entire history of life on Earth, though tidal locking and stellar flares will shape their environments in ways still not fully understood. The quiet mystery is how such worlds will fare in a universe where the frequency of supernovae and other disruptive events has dropped, leaving a calmer but dimmer sky. White dwarfs will continue to cool their luminosity, fading as they radiate away their stored heat. Over time, crystallization will proceed through their interiors, and their spectra will shift toward the infrared until they become black dwarfs emitting almost no light. This cooling process will take longer than the current age of the universe by many orders of magnitude, making these cold remnants a feature of the deep future rather than the present. The irony is that the processes governing their cooling are well understood, yet their final states are inaccessible to observation for now. Neutron stars will persist almost unchanged in structure, slowly losing any residual heat and magnetic activity. Without accretion or mergers, they will be nearly undetectable, their presence inferred only from gravitational effects. Some will drift in interstellar solitude, while others may remain bound in binaries, their companions evolving slowly beside them. Black holes too will endure their gravitational pull, unchanged their mass constant except in the rare event of mergers or accretion. Over trillions of years, gravitational interactions may eject many neutron stars and black holes from the galaxy, entirely sending them into the intergalactic void. In the galaxy's core, stellar orbits will evolve under the influence of gravitational encounters, leading to the slow migration of remnants toward the center, where they may be consumed by the central supermassive black hole. The quiet mystery in this era lies in the dynamics of such remnant-rich systems, where encounters between compact objects could produce rare mergers even when star formation has ceased. Over immense timescales, the orbits of stars and remnants will shift due to gravitational encounters, altering the structure of the galaxy. Globular clusters may dissolve entirely their members, joining the general stellar population, while faint streams mark their former paths. The spiral structure will fade as differential rotation blurs the arms into a smooth disk, and the distinction between disk and halo will soften. Without fresh infall of gas, the galaxy will slowly lose the capacity to form new stars, entering a phase of gradual dimming. The irony is that the chemical richness built over billions of years will remain locked in the remnants, and the cold interstellar medium unspent in new generations. A second irony is that the galaxy's mass in dark matter will remain unchanged, so its gravitational potential will persist long after its visible light has dwindled. The third irony is that while the luminous phases of stars make up only a fraction of the galaxy's history, they define its legacy in the record of elements left behind. Even in this diminished state, the processes that once drove stellar evolution will not be entirely absent. Occasionally, gravitational perturbations may cause a remnant to encounter a reservoir of gas, triggering accretion and a brief flare of activity. Rare binary mergers of white dwarfs, neutron stars or black holes will still occur, producing brief flashes of light or bursts of gravitational waves that ripple across the quiet cosmos. In some cases, tidal interactions between remnants and planets or brown dwarfs may strip material and produce detectable signatures. These isolated events will punctuate the long stillness reminders of the energetic processes that once dominated galactic life. Only took a few billion years of intense star formation to populate the galaxy with the seeds of its far future. Only took the inexorable workings of gravity and nuclear fusion to transform hydrogen into a tapestry of worlds, elements, and remnants. Only took the passage of cosmic time to shift the balance from light to shadow. In the grand arc of the universe, the life cycle of a star is one of the most consequential patterns shaping the evolution of matter from the simplest to the most complex forms. The early universe saw the first stars form from pristine hydrogen and helium, their lives short but their influence immense. They forged the first heavy elements, set the stage for galaxy formation, and began the cycle that continues to this day in galaxies rich with variety. The present era still holds active star formation, but the seeds of decline are visible in the gradual depletion of cold gas and the aging of stellar populations. The far future will be defined by the slow fading of starlight, the cooling of remnants, and the dispersal of galaxies over expanding space. The quiet mystery that remains is how many cycles the galaxy can complete before its gas is too thin and warm to form stars at all, and whether some future collision or inflow could revive the process in a diminished form. The elements forged in countless stellar cores will endure far longer than the stars themselves, drifting in molecular clouds or locked into planets, asteroids, and icy bodies. They will remain as silent witnesses to the transformations of the past, carrying within their atomic structures the story of fusion, death, and renewal. In this way, the life cycle of a star is not just a sequence of stages, but a continuing contribution to the evolving universe, linking the most fleeting bursts of light to the most enduring forms of matter. In the dim reaches of time, when the galaxy has grown quiet and the night sky has thinned, the remnants drift in their patient arcs unhurried by the loss of their makers. White dwarfs cool toward blackness. Neutron stars lie in the deep cold between suns, and black holes travel unseen, each one holding a story that will never be told in light again. Red dwarfs still burn in slow measure, their faint warmth enough to keep their worlds in orbit, and their gravity bound to them, but the crowd of stars that once filled the sky has long since faded into a sparse scattering. Gas clouds have grown thin and rare, their atoms reluctant to gather, their motions too languid for collapse. There is no rush to the cycles now, only the long rest between what has been and what will never quite return. The quiet that settles over such a galaxy is not sudden. It is the slow lengthening of stillness, the softening of all the restless processes that once marked time in bursts of fusion and flares of light. The dark matter halo still cradles the fading structure unseen, but holding its shape even as the luminous parts lose their strength. Across the void, other galaxies retreat, their light red-shifted into wavelengths too long for ancient eyes to see. Gravity still binds what is close, but space itself carries the far away beyond reach. The chemistry of the past remains in every remnant, every frozen fragment of rock and ice, every atom of oxygen, carbon, iron, and gold, a record etched in matter long after the light has gone. And though the cycles have slowed, their work is finished in a way that does not feel like an ending, only a settling heat into cold motion, into drift brilliance, into a memory that does not fade but simply becomes part of the whole. In such a night there is no need for beginnings or conclusions, only the weightless passing of time, the eternal curve of orbits, the unbroken silence between the stars. In that silence there is rest.